Welcome back, everyone, for part two. I will not recap part one, but we spoke about scalar curvature and lower bounds on scalar curvature where sigma was taken to be either 0 or positive. Now, as I mentioned earlier on, in relativity, the main object of study are Lorentzian manifolds, n+1 dimensional Lorentzian manifolds. These satisfy the Einstein field equations, right, which look as follows. And T is the so-called stress energy tensor associated with the possible matter fields in the space-time sources, if you like, for the left-hand side, which is purely geometric. And when you take the Gauss-Kadatsky equations for hypersurface, kind of space-like hypersurface embedded in the n+1 Lorentzian manifold, you end up with the following set of equations, which are called the constraint equations. Constraints because these are necessary for MGK, this Riemannian manifold, to embed into the Lorentzian manifold, and K here is the second fundamental form associated with that embedding. G is the induced metric on Mn, and the mu and J here appearing here are just particular contractions of this stress energy tensor. Now, the reason why you might think of this as kind of relativity's generalization of lower bounds on the scalar curvature is because actually you tend to assume that T, these matter fields, are reasonable in some sense. They source the gravitational field in a reasonable sense, and that means they satisfy some energy conditions. Comes from the intuitions of physicists, comes from typical results, typical matter models used. And one in particular that's very useful is called a dominant energy condition. And that is a condition on T, which transpires at the initial data level to a condition that mu is larger than the absolute size of J, measured right with little g. And if you actually write that out, then you get the scalar curvature here, an inequality here, and all these terms appearing on the right-hand side. So it's like this, but this term is no longer a constant, right? It depends on all kinds of things, which themselves depend on the metric and depend on the second fundamental form. When K is 0, all of this dies, and we're just in the Riemannian setting of lower bound on the scalar curvature, 0 lower bounds on the scalar curvature. So for these more general spaces, these initial data sets, there still exists a positive mass theory. And in fact, that was first shown by Shane Yao in 81 and Whitten in 81 at the same time. And the proof is quite a bit harder than the Riemannian one. And sometimes it actually reduces it to the Riemannian one. So there's different proofs. But we'll be looking at kind of geometric arguments, so not spinorial kind of arguments, that generalize the Riemannian arguments, and where in particular a certain class of surfaces called marginally outer trapped surfaces, so the acronym is MOTS for marginally outer trapped surface, which again is going to be, I'll describe why it's called that. But anyway, these replace minimal surfaces, which you know we saw in the first part of the talk, right? In this Shane Yao sketch of the argument, right? The plateau solutions, minimal disks, taking the sequence of minimal disks, etc. So these are minimal surfaces, but in this setting, these surfaces will replace minimal surfaces because minimal surfaces just don't track some of the extra information that you deal with when you deal with this initial data, which comes from K, so the second fundamental form. So in this setting, you can define an energy and a momentum. I'm not going to define these. The energy is the same definition as the mass, but the momentum is as we talked before, but the momentum is different, and so you can ask the question of whether or not as a vector is this vector time-like or right, and if it is, then you say the mass is E squared minus P squared, right, in the typical relativistic setting, and so the theorem in this case says that actually E is larger than the absolute value of P, and moreover, equality only occurs in the trivial case that both equal to 0 and the initial data embeds in the Minkowski space. So this is a fundamental result. And as I said, mods replace minimal surfaces. So what are mods? So in Lorentzian geometry, a space-like submanifold of codimension 2 now is associated with two null second fundamental forms that track how null geodesics emanating outwards and inwardsly, say if it's two-sided, from the surface, how they change or how the submanifold embeds in the space-time, right? So that's the definition, right? L plus, L minus are null normals. X and Y are tangent to sigma. They live in the tangent space of sigma, and then this is our expression for the null second fundamental forms. Taking the trace over sigma, you have what's called the null mean curvature, which is just the analog of the usual mean curvature in Riemannian geometry. And if you expand it in its components, it has a kind of typical H Riemannian component, and then trace K projected onto sigma, where this is the, comes from the embedding of the sigma in the initial data set, which itself embeds in the space-time. So by looking at typical examples of space-time, like the Schwarzschild solution, things like that, you can find surfaces that are trapped, which means that the null expansion is strictly negative in both directions, the outer and the inwards going. And you find this in the interior of black hole regions and things like that. And then when one of the directions, the outwards in particular, is 0, then we say it's marginally outer trapped. Outer because you pick just one direction, the outer one, and marginally because it's not an inequality, it's an equality. So that's why. And notice, of course, that when K is 0, I should reduce back to the Riemannian case, and these mods just become minimal surfaces. So right, these are 0, these terms are 0, and then I just get H equals 0. So this is a picture. This is the initial data set. This is the space-time. This is sigma embedded, right, as a hypersurface of M, but actually also as a codimension 2 submanifold of M bar M plus 1. And these are inwards going and outwards going. So inwards going and then outwards going null geodesics. And so they've got L plus and L minus as the null normals, and I can associate a second fundamental form associated with these directions. So what happens when I vary? So remember when we had these minimal surfaces, they were used before because of the stability inequality, right? Because we minimized in some homology class that gave us a stability inequality, and the stability inequality was used in various ways to prove various things. So how is something going to happen in this context? What are we going to study? Well, the second variation, which is the stability inequality, comes essentially from varying the first variation. And the first variation is of course right, the condition that the mean curvature is 0, and so expanding or varying the null mean curvature right in the direction normal to the surface is kind of asking what happens to the null mean curvature as I move these surfaces normal in the direction of the initial data to the surface. And when these when this is non-negative, then we know that this expansion is or these mots are basically, in a way, they're if you move outwards, they're not going to become trapped essentially. But if you actually do this computation, you actually expand, this, and you see what you get. You identify this operator L of phi. Phi is just right, comes from the variation vector field. So n is the normal. Now n is the normal. Before I was using a different letter, but anyway, you get this huge mess. And when theta plus, which is the right null mean curvature 0, these terms die. But you still get, this term, and this term in W here is this kind of extra term that comes from the, right, so W is a one form that comes from the contraction of K with Y and N, where Y is just some vector field in the tangent space of sigma, and N is this normal. So Q, I've written here, as just one letter, but actually Q is a bunch of curvature terms, right? So this is mu coming from the constraint equations, right, from the previous slides that we saw here. So this is this mu, and J is again J that we saw before. And then here's a scalar curvature of sigma and the null second fundamental form in the outwards direction. Okay, so that's what happens when you vary the null expansion. And you can then show actually that L has a real principal eigenvalue. This takes some work, but you can do it. And once you've done that, well, then you can define stability by saying, well, I suppose the eigenvalue, right? The principal eigenvalue has well, it has a real, right? It's a real eigenvalue. So you can just say, right, suppose it's non-negative. Then you call this mod sigma a stable mod if that's the case. And then you might say, okay, well, what good is this operator, right? Because it's so complicated. It's got so many terms. Well, actually, by a very nice computation by Galloway-Shane in 2005, you can actually show that there's another operator called the symmetrized MOTS operator, where now all these other terms has been, all you're left with is Q, right? And Q is just a bunch of curvature terms here. Right, anyway, so you can show that this inequality holds for a stable mod. So if it's stable, then actually the eigenvalue, the principal eigenvalue associated with this very nice operator, L0, the symmetrized stability operator, is non-negative. So then if you say, well, suppose in addition the dominant energy condition holds, well then notice that this term has the same sign, right, because there's a minus in front of it as this term. So you end up with just the scalar curvature of sigma minus some terms with a sign, right? They all have a sign. So in particular, I've written it like this, you know, it's you know, so minus some absolute number, right, absolute value. And then so in the stability inequality, because you have got this inequality, right, you can move this on the right-hand side. And then suddenly you've got terms involving the Laplacian and the scalar curvature on the left-hand side. And you have a positive low, right? You have a positive low bound from the inequality. And so that's very much reminiscent of what we saw in the first few slides, right? Of the stability inequality in the Riemannian setting. And indeed, this is exactly what happens. So there are a number of properties that are analogous to those obeyed by stable minimal surfaces in ambient Riemannian manifolds with lower bounds on the scalar curvature when you assume the dominant energy condition. So this is a kind of a good analog of the non-negative scalar curvature. So in addition, there's a very nice existence irregularity result for marginally overtrapped surfaces. So suppose MGK is a compact smooth initial data set with two boundary components, and suppose that the null expansion on one of the boundary components computed right, that's pointing into M is negative, and suppose that pointing out of M on the outer boundary component it's positive. Well, then you can show that there's an embedded stable MOTS homologous to the outer, we call this untrapped boundary, which is now measured in the same direction, right? That points towards partial 2 of M. There is a dimension here, so N is less or equal to 7, right? Because if you don't have this, you know, if the regularity for minimal surfaces doesn't work, and these surfaces are kind of analogous, you shouldn't expect the regularity to work. And indeed, from the perspective of integral currents, these are actually lambda minimizing, and that means they minimize n-1 volume up to an n-dimensional volume term multiplied by a constant lambda. So they're not minimizing, but they're minimizing up to a volume term. So notice here that it's embedded and it's stable, right? And those are two very good things to know. And it's homologous to the partial 2 of M. That's very good things to know, because once it's stable, then we know that we can apply some of the tricks that we saw before with this MOT stability inequality and the symmetrized MOTs, and reminiscent of the first few things we saw. So now I want to talk about another version of Lokhamp's trick, but a slightly harder one this time, but for initial data sets. So before, remember, we had the Shen-Yao argument for the positive mass theorem that involves studying the plateau problem, taking a sequence, and then, you know, having to deal with the non-compactness of the space fully. But then Lokhamp showed that actually by compactifying, by having nice asymptotics, you can compactify in a suitable way and reduce the positive mass theorem, or at least one part of the positive mass theorem, to a geometric theorem. Well, it turns out that Lokhamp actually argued this for the initial data set setting in a very, it's a very nice argument, which essentially tells you that if the asymptotics are good enough, again, you need good asymptotics for these kinds of arguments, that if the initial data set version of the positive mass theorem, right, if it's false, then you can produce an island, compactly supported region where mu minus j is positive on the connect sum of Rn with Zn being a compact manifold. So the idea is that suppose the positive mass theorem is false for initial data sets, then you produce an island. And so if there are no islands, then the positive mass theorem has to hold. And I've used R here, but really, once it's flat, then it's irrelevant, right? I could just use the torus because I can identify the sides of a large cube in the flat end. And so essentially, this is what happens when you identify a large, you know, the size of a large cube in the flat end. And so if you can prove that such a thing can't exist, if you can prove that this is not allowed, that you can't have an almost flat everywhere torus connect sum with a compact manifold having dominant energy scalar positive, so mu minus j positive in this region. If you can show that this is not allowed, then you've shown that the positive mass theorem for initial data sets works. So this reduces the positive mass theorem for initial data sets to a geometric theorem. And the other proofs for the initial data set version of the positive mass theorem do not go this way, and they actually deal with the non-compactness of the space, you know, straight, like in a direct manner, which can be hard, right? We can introduce a lot of difficulties. And so then one reduces the statement to proving a geometric theorem, and Lokhamp does this, at least for n is less or equal to 7. For high dimensions, I don't understand the arguments, so I don't know if this works, but at least for n is less than 7, the regularity is fine, and this geometric argument works. And you can say, you know, suppose x at n is compact, then there cannot be a mu minus j island on the torus xn, where, remember, this is organized in this setting. This is organized so that the torus is flat outside of the n minus one dimensional tori that appear in this picture. Right. So how does this argument go? Well, first you kind of have a deformation argument that produces two copies of these n minus one tori having the right null mean curvature. In particular, by right, I mean something that you can apply this existence and regularity result so that you can then obtain a MOTS by that result, and the MOTS will lie somewhere in the middle. So somewhere around here, there will be a MOTS. This MOTS will be stable because of the result I just showed you. That follows from Metzger. And you have a compact embedded stable MOTS now in a region where the DEC is satisfied strictly. And once you have this, well then, right, let's go back to this stability inequality. These terms all have the right sign. You can throw them on the other side. You get half the scalar curvature, Laplacian, you integrate, and you've got yourself the stability inequality, and sigma is now Yamabe positive. But that cannot be because you're homologous to these outer untrapped boundary, the Tn minus 1, in the manifold Tn connects some xn. And that's a contradiction from classic results, right? From what we saw in the first part of the talk. So that's the geometric theorem of Lokhamp, and that's the proof of the positive mass theorem for dimensions less than n in the initial data set setting. So this is a very clever, very dexterous argument. Well, what we did with Ryan and Yao is show that actually the geometric part of the theorem, so this part, we don't know, if this works, if there's a reduction of the positive mass theorem with arbitrary ends for the initial data set setting, that's unknown. I believe that's open. Nobody knows how to compactify that in some way because handling the non-compact ends is hard. And so what you can show, however, is that a geometric version of the theorem, so this theorem, you can replace this by something non-compact, right, in dimensions n equal to 3. So that's what we show. So we show that in the three-dimensional case for x is arbitrary, you can't have diagrams like this. So now you have a torus. It's still mostly flat, but you've got these two tori, and then you've got this region where mu minus j is positive, and this could be asymptotically flat, asymptotically hyperbolic, cylindrical, periodic, whatever. And then you show that indeed this can't happen. Such a diagram doesn't exist. Well, it doesn't work. So it's kind of analogous to the Riemannian theorem, right? So in part 1 of the talk, we saw that this right, positive mass theorem with arbitrary ends, and then we saw that you can show that indeed you can't have manifolds of this kind, where now you had Schoen-Weyl-Schick connect some with an arbitrary manifold. Schoen-Weyl-Schick is of course much more general than just the torus, but in the initial data set setting, we prove it for the torus because that's kind of the clear case of interest. And so it's analogous to the Riemannian sense, to the Riemannian proof, because we do this exhaustion just like we did before, and then with the right sign on the null mean curvature on the boundary components, you show that this MOTS kind of avoids the boundary. But then as you take the exhaustion higher up, the MOTS could potentially grow, and so it could kind of grow. And as it grows, you've got the stability inequality that is going to be ultimately what you're going to get your contradictions from, and you're going to show that having a strict mu minus j is going to give you a contradiction with the stability inequality on this limiting hypersurface, and this in general can be non-compact. It turns out not to be, but that's something you actually have to show. And the reason why this is only for the three-dimensional case is because for the high-dimensional case, remember, we have to deal with this lambda rho contractibility to ensure that the sequence ended up being compact, but such a thing doesn't work here, at least not in any obvious sense. So that's why it's only three-dimensional. And then, if you think about using new bubbles, well, then that's interesting, but that's not something you can do straightforwardly. You need some stability inequality that listens to K in some suitable sense. So then you use, right, so you use, how do you actually prove, once you have the stability inequality on a MOTS, which could, explore the ends, you use results, rigidity results of Galloway and Shane and Carlotto to show that you get a contradiction. So I think it's time for me to finish the talk, and I just wanted to finish with some kind of concluding remarks about the kind of landscape that we know about these results, about scalar curvature and about positive mass theorems and about initial data sets and so on. So first we have that, the positive mass theorem and the torus theorem, if you like, the compact torus theorem is shown by Shane Yao in 79. So at that time, it was known that there's no PSC metric on torus connects some with a compact manifold, and the positive mass theorem for non-negative scalar curvature was shown. And so these were two, different papers, very, beautiful discoveries. Then in 81, Shane Yao proved the positive mass theorem, or a version of the positive mass theorem, for initial data sets. So dominant energy condition replaces scalar curvature bound. And of course, this implies the original one. And the proof actually works by reduction to the original one. The more recent proof in 2015 by Ishmael Hong Shane is kind of more delicate and involves the original Shane Yao argument of taking the limit of minimizers, but in this case, the limit of MOTS. So that's the landscape in 81 or 2015, if you like. In 88, you've got you've got the work of Shen Yao that tells you that the arbitrary ends version of the positive mass theorem, so that's all but one ends are asymptotically flat for non-negative scalar curvature. If this were true, that would imply the injectivity of phi, right? That's what was done in 88, and that's why this conjecture was motivated, but I don't put a box around it because it's not known. Then in 99, Lokhamp actually shows that, in fact, the positive mass theorem just follows from, right, so Lokhamp does this. He shows that the geometric theorem actually implies the positive mass theorem. And that was the, the trick that I showed you before, right? So using the asymptotics to compactify and then producing a PSC metric on this manifold, and then, showing it's not allowed by the geometric theorem. So that's in 99. And then in 2020, you've got a kind of sprawling diagram. So this geometric theorem now gets generalized by Chodosh Lee without assumption, at least for the torus case. And then by us using an assumption for dimensions 4 to 7 in the torus case, but covering a larger class of manifolds, simply Shin-Yao-Schick manifolds as opposed to Shin-Yao-Schick cross S1. So that's that story. Then we show that this actually implies that phi is injective. So now phi is injective. That's known now, right? But the arbitrary positive mass theorem is still open. So that's for the Riemannian case. And then in 2016, Lokhamp gives the reduction of the islands, right? The islands initial data, right? No DEC islands on compact manifolds of this form, right? Torus connects some with compact manifold. That now implies the positive mass theorem for initial data sets, right? So that's the analog of this trick here. Let me get rid of some of the circles. So now the positive mass theorem for initial data sets is a corollary of the geometric theorem of Lokhamp. And the compactification trick is Lokhamp's argument. And then just like Chodosh Lee or Ryan Yao and myself show that actually you can generalize this geometric theorem to the non-compact setting, the same thing happens with Lokhamp's geometric theorem. So now this gets generalized to the non-compact setting by Ryan Yao and myself. But of course it motivates, what about the arbitrary end version of the positive mass theorem for initial data sets? So that's totally open. And of course this now looks like it's well, if it were true by Shen-Yao 88, it would imply that phi is injective, but we already know that phi is injective from our result and that of Chodosh Lee. So that kind of, is good motivation to try and prove these two conjectures, which I now leave in circle. All right, so thank you very much for listening, and I look forward to your questions. And thank you again, Professor Lee, for the opportunity to speak.